All right, so we're gonna get started on chapter 10. In this chapter, we're gonna look actually at one of the most important applications of number theory, that is to the area of cryptography. The word cryptography actually is derived from the two Greek words, cryptos, which means hidden, and griffin, which means actually to write. Informally, cryptography is the study of the methods of sending messages in disguised form, so that only the intended receiver or recipient can remove the disguise and read and understand the message. So in some sense, this involves transforming the message into apparently unintelligible garbage, sort of, so that unwanted eyes will be unable to understand it. However, this transformation must be done in such a way that it is reversible. That is, so that individuals intended to review the information can do so. So we're going to begin in this section by first introducing some terminology. Okay, so that we can talk about cryptography and define it formally. And then we're going to look at some classical cryptography or what we call the cryptosystems. So the scenario goes like this usually. We're going to consider two parties, Alice and Bob. These could be individual, these could be actually organization, companies, banks, and so on. Alice wants to privately send a message to Bob over an insecure channel. And by an insecure channel, such as a telephone, or could be actually over the internet, and so on. The message or information Alice wants to conceal means doesn't want other people to understand, is called, before it conceal it, is called the plain text, or sometimes we call it the clear text. Of course, Alice and Bob would like their privacy to be maintained, even in the face of an adversary, which we refer to it as Eve. And Eve actually is coming from eavesdropper, that may intercept the message with bad intention in mind. For example, Bob could be actually Alice's bank. Alice wants to check her account balance, and Eve could be somebody who would like to intercept Alice's password so that he could take money from Alice's account. And there are many other examples you could think of. So the idea of cryptography is to transform the plain text. It could be a message, it could be data, in some way, so that when Eve intercepted, she will not be able to understand it. Now, the transformation Alice applied to the plain text is called Ciphering function or encryption function. The encryption function changes the plain text message into another kind of message, which is, again, it's like looks like garbage. It's called the ciphertext message. Now Alice sends the ciphertext message to Bob. Now Bob, when he receives the ciphertext message, apply another transformation to the sphere text message. And this transformation is called despheering function or decryption function. And to convert it back from a sphere text to the original plain text or clear text. So this is informally the sort of what's going on. Now we're going to define or formalize the above discussion by defining what we call a cryptosystem. So a cryptosystem, or sometimes we refer to it as an encryption scheme, is a tuple consists of the following set of data. The letter P, which we're going to define, the letter C, K, this E, and D, where P is a set, and we refer to this set is called the plain text space. The elements of this set are called the plain text. This is just what the messages kind of, or the data that we need to transform and actually send over insecure channels. The second set is C, and we refer to it as the sphere text space. And the elements of this set are called sphere text. The third item is K, which is a set. It is called the key space. The elements of this set are called keys. Then we have this letter E, and this consists of a family of functions, E sub k for every key, small k in k. E sub k is a function that associate, or it goes from, whose domain is the plain text, the set of plain text messages, to the sphere text messages. And its elements are called encryption function. And another set of functions, which we refer to as D, and it consists of the set D sub k. K in K is a family of functions that goes from C to B. Again, the K for the encryption is different in general than the K for the decryption. Just in here is just we are using the simple abstraction. The elements of this family of function we refer to as despheering or decryption functions. One other property that we want these functions, for each one of these functions to satisfy, that for each E in K, there is a D in K, so that when we apply the first, we start with a plain text and apply the encryption using the key E, then followed by decryption using the key D, then we get back to the original message, actually, P, for all P in P. All right, so next we're going to introduce some classical crypto systems. One of the earliest crypto systems was used by the great Roman Emperor, Julius Caesar. This was around 50 BC. This type of crypto systems are called Caesar crypto systems or Caesar spheres. In these crypto systems, the plain text space and the space text space and the key space are the set of alphabets for a certain language. So if we go with the English language, then it is A, B, up to Z. We could also have some other characters added to this set, but we're gonna restrict ourselves to some simple Caesar crypto system, and we're gonna consider the plain text, sphere text, and the key to be actually just the alphabet from A to Z. So the first step, and this is true in almost all the crypto system that we're gonna talk about, is to convert the letters into numbers. And one simple way to do this is to associate with every letter a 2-digit number. A, we're going to associate with 00, B, 01, C, 02, up to Z, 25. This allows us or enable us actually to compute, use actually modular arithmetic, as we're going to see, to define the encryption and decryption functions. So for each, the way, we do the encryption, we take a key in Z26. Z26 are actually the numbers from 0 to 25, all right? And the encryption function E sub E is given as a function from Z26 to Z26, which associate with every letter X, the X plus E mod 26. So in other words, in terms of letters, we are just replacing each letter by another line down the alphabet. For example, A, we could actually substitute for it the letter H, all right, and B, the letter G, and so on. So we just do a fixed shift of the alphabet down, going, from left to right. Similarly, for a decryption, D key 26, the decryption function is take X and subtract actually the D. So in the Caesar's crypto system, actually the encryption key and the decryption key are the same. The same D is equal to E. The only thing is the way the function is defined. One, we do addition of E mod 26. The other, we do subtraction of the same number mod 26. Now, so far we defined the Caesar sphere only to, or the encryption and decryption function for single letters. It's not very hard to actually modify the Caesar sphere so that you can apply it for a block of letters. Mathematically, which means that we can apply the Caesar sphere to sequences or vectors, W, which consists W1, W2, up to Wn, where each one of these W is actually one of the alphabets, or their numerical equivalent, means a number taken from Z26. And the encryption function, we apply it at each component, all right? So we replace each WI by WI plus E mod 26. And we do this one for every I. All right, so let's look at an example. This is a very simple. So if we apply the Caesar sphere with a key that's equal 5 to the plain text cryptography, then we obtain this these alphabets or these letters, as you see, they are meaningless. If someone, intercept, they will say, well, this is just a garbage. However, if the person that is receiving this message know that the key used is 5, then all what they have to do is, again, write the equivalent numerical values for all the letters in the sphere text and subtract from that 5, then they recover the original message. So the Caesar's actual sphere uses only 26 keys, because if we only, of course, using the alphabet from A to Z. So it is therefore very easy to determine the plain text from the sphere's text by trying all possible keys and checking by which plain text makes sense. So in other words, this is very easy to break or to attack, what's called, by trying E equal 1, 2, 3, up to 26, and then do the the despheering or decryption of a sphere text. And of course, if it makes sense, this means that that the original clear text, what it is, or plain text, and then you would know actually also the key. And then you can also, besides knowing the message, you could alter the message, all right, and this of course becomes very dangerous. So in fact, Caesar himself quit using this system because it turned out to be not actually secure. The encryption method of the Caesar sphere consists, of course, of replacing each letter in the message with one that is a fixed number of places down the alphabet. So in other words, encryption is a cyclic shift of a fixed number K, which is the key, on each letter in the message. So each letter in the message, it will be, in other words, replaced by another letter, and it will be the same throughout the text. So if A is replaced by H, then if there is another A appears in the message, it's going to be again replaced by H, and so on. So in this case, in each letter in the message, and the decryption is a cyclic shift, of course, of negative K. So for this reason, we refer sometimes to encryption schemes or a crypto system of this kind, and Caesar sphere is one of them, as substitution sphere. Because we just are substituting letter by another letter, and this substitution is for a particular key is the same. All right. Another way to characterize the Caesar sphere, as we call it, monoalphabetic substitution sphere. And there are other crypto systems that are of this nature or of this type. And the word mono means one. So a monoalphabetic substitution sphere is one in which a single sphere is employed throughout the whole message, and each character of a message in the plain text is replaced with a unique character to obtain an encrypted message. So another way to say this, so in other words, the encryption function is one-to-one. So, and now the Caesar A sphere, as we've seen, uses actually modular addition to encrypt each letter of a plain text to a corresponding letter of a sphere text. Another example of a monoalphabetic substitution sphere is to use modular multiplication. So instead of taking an alphabet or a character and add the key to it, here we multiply and of course do mod 26 multiplication. So for each E in Z26, the encryption function E sub E is given by applied to X is actually EX mod 26. And the corresponding decryption function is by multiplying by the multiplicative inverse mod 26 of E. So we just multiply X by E, this -1, which is multiplicative inverse mod 26. Now, as we know, not every element in Z26 has a multiplicative inverse. In order for it to have a multiplicative inverse, E must be relatively prime to 26. And the reason for this, because we could see that, different letters, they could actually will be encrypted and they give us the same letter, which means that we will be unable to decrypt the message. So for example, if we use a key of 2, then B, it's gonna go to 2 multiplied by 0, 1, which give me 0, 2, that is corresponds to C. And the letter O, its numerical equivalent is 14. And if I multiply 2 by 14, I come up with 28. And when I reduce this mod 26, I come up with 0, 2, which is C. So for this crypto system, if I use this key, then B is gonna encrypt, it will be encrypted as C, and O will be encrypted as C. So when we're gonna decrypt, then we're gonna have a problem with this. So in other words, this E2 has no inverse. So in general, for a multiplicative sphere, a key E must satisfy this property that the numbers, when I multiply 0, of course, E times 0, mod 26 is 0, then E mod 26 and 2E mod 26 to 25 times E mod 26. These must be all distinct in order for the for E to be a legitimate actually encryption key. So he said this is in a form of theorem that is for these to be distinct, means to give us a one-to-one encryption function. That's really what also it means. Each letter is gonna encrypt to a single letter. We don't have, two different multiplication with E, with the numbers from 0 to 25 give us the same result. This is guaranteed if the greatest common divisor of E and 26 is equal to 1. And here is the proof. It's very simple proof. Suppose that we do have the greatest common divisor is equal to 1. And let's assume we have two different letters and their corresponding numerical equivalent is X and Y, and between 1 and 26. Actually between 0 and 25. And want to show that EX is not congruent to EY mod 26. And we can do this by contradiction, assume they are, then we write this congruence relation as an equality relation. for some k in Z. Now, since the greatest common divisor of E and 26 is equal to 1, then X minus Y must contain all the factors of 26, which are 1, 2, 13, and 26. However, X minus Y is strictly less than 26, so X minus Y cannot be a multiple, as this statement is saying, of 26, and then which means that these are actually distinct. For the multiplicative sphere text, this set of possible keys are the relatively prime numbers to 26, which are 1, 3, 5, 7, 9, and so on. So this is a very limited number, of course, of keys, and which means even the this crypto system that's based on modular multiplication is even less secure than the additive one. Now we can combine both the modular addition and multiplication to come up with another crypto system. Is called affine spheres. And this is another example of a monoalphabetic crypto system. And this can be obtained by, again, combining the addition and the additive and multiplicative spheres. And in this case, the key consists actually of two numbers. If again we use only the English alphabet from A to Z, so these are going to be two numbers from Z26, and the key space consists of these ordered pairs, where the A, which is going to be actually the multiplicative key, to be relatively prime to 26. So the encryption function in here, E, which is associated with every key A and B, is given to be E sub A, B from Z26 to Z26, which is just this linear sort of combination, AX plus B. And the plain text, the sphere text, and as we've seen, almost the key is Z26. Actually, the additive key is Z26, but the multiplicative is those integers which are relatively prime to 26. The decryption, we do the inverse of A, the multiplicative of inverse of A minus 26, and the additive inverse, or subtracting basically B. And the decryption function, it is formed like A inverse, parentheses X minus B mod 26. Here's an example. So let's assume that Alice chooses the key 7-3 to encrypt the word bad with an affine sphere. So B is equivalent to 0, 1. So we do multiply by 7 and add 3. So this gives us 10, which is the letter K. And then the A goes to the letter D, and the D is assigned to letter Y. So the sphere text is going to be KDY. And Bob, once he receives the message, can be encrypted like this and get, of course, the original message back. Now, if we want to count the maximum number of keys for an affine sphere text with this alphabet from A to Z, it's going to be because it's ordered pairs, so it's going to be the number of the A's, which is going to be 12. Those are numbers relatively prime to 26, multiplied by the additive keys, which are 26, so a total of 390. So it's a bigger key space, but again, exhaustive, what we call attack, We can, in other words, do trial and error. We could try all these, keys if we intercepted a sphere text, and we could determine the actually what the message is. All right. In fact, if we know it's easier even to attack this affine crypto system. If a non-plain text attack is used and two symbols only, together with their encryption, are known, then the affine sphere can be broken. Means if I know just one symbol in a plain text, what it translates to, or what's its sphere text corresponding letter, two of those, then by use of just basic algebra or linear algebra, we can find the the encryption and decryption key. So here it is. Let's assume that the letter A is encrypted as R. So this is one letter. And the letter S is encrypted as H. Now, let's assume we have this information. Then we have these congruences. And let's assume that we use the letter E to be 4. And so we have the transformation is going to be 4A plus B. Okay, so this is the first key, the multiplicative key, and this is the additive key. This gives me 17, which is the letter E here, and this is R. And also we know that 18A plus B give me 7, which is the H. Then by taking the first congruence and actually solve for B, and then substitute in the second congruence, then we obtain a linear congruence equation, which we can solve. And then we can determine that A is equal, in fact, to 3. And then we could find B is equal to 5. So very easy, even we don't need even, just a very limited information can break this crypto system. All right. Now, in the problem with the monoalphabetic substitution sphere that we introduced, the key space was relatively small in size and can be attacked by what is called exhaustive key search. We could try all the keys. So one way to improve the security of this type of crypto system is to make the exhaustive key search infeasible by making the key space very large. All right. And here is one crypto system where it's very hard to break using what we call exhaustive search, means try all possible keys. And this is called permutation spheres. Now, this is a different kind of crypto system. It does not involve this substitution, means you substitute the letter by another letter. In here, we use actually the same letters, we just rotate them in some sense. So, so in here, what we do is we replace the different sphere text. The idea of the idea of the permutation sphere is to keep the plain text characters unchanged, but alter their position, all right, in the message by rearranging them using a permutation. Well, let's recall what a permutation is. A permutation on a finite set X is a bijective function, means a one-to-one and onto function, pi from X into X. So the permutation sphere is also known as the transposition sphere, is defined formally like this. So we're going to let M be a positive integer, and the sphere text and the plain text and the sphere text is Z sub 26. It's actually the Cartesian product of Z26 by itself M times. So in other words, this is going to be sort of sequences of numbers which are coming from letters of length M. And we're going to let K consist of all the permutations of a set in M letters or M symbols. We can think of it from 1 to M. For a key that is a permutation, pi and k, the encryption function is you take this sequence, okay, which is again part of a message, and replace each one of these by the first one, the first letter or the first number in here, by the permutation where this permutation pi take 1 to. All right, remember that pi is going to be a one-to-one and onto function from 1 to M. And so it's going to permute just the letters or the numbers that appear in the message. Their location is going to be just mixed up. And the decryption, we just apply the inverse of this permutation. Remember, pi is a one-to-one onto function, so it does have an inverse. Here's an example. Suppose we partition basically the message into blocks of length 6. And let's assume we take the permutation given by where 1 goes to 3, 2 goes to 5, 6 goes to 2. And let's assume that the message that we're going to encrypt using this permutation is she sells seashells by the seashore. First, we partition this message into blocks of length 6. And then we apply the permutation and then write the numerical equivalent of these letters. And or we could actually translate another way to these numbers. I'm sorry. Actually, we're gonna think of let me track back in here. So when we're gonna apply pi, we're actually gonna think of, we are not using what is called the numerical equivalence of the letters in here, only their position. So S is going to be in the first place, H is in the second, E in the third, fourth, fifth, and sixth. And then we're just going to rotate these based on this permutation. And we're going to do it for the second block and so on. So when we do these, the S, which is the first, is going to go to the third. And the third here is E. So you're going to see that E is going to appear first, and then the H is going to be the second, and second goes to the fifth, and the fifth letter in here is E is also, and so on. So we just permute again each block, all right, based on the position of where these letters. And when, of course, we apply the inverse, we get obtain the original message. The other part of that we are concerned with in cryptography is called the crypto analysis. These two branches, basically cryptography and the crypto analysis, they form what is called the cryptology. So cryptology consists of these two disciplines. And the crypto analysis is the different methods of attack or trying to break a crypto system. And there are different types of attacks. I don't want to go through the whole thing in here. The simplest kind is where it is called sphere text only attack. So in this type of attack, the attacker knows a sphere text. So it just intercepted a message and it tries to recover the corresponding plain text, or means to decrypt it, or even further to find the decryption key. Another type is called non-plain text attack. So in here, the attacker knows a plain text and the corresponding sphere text. So he knows a match, a pair of plain text, and what is actually the sphere text of it. Or he could have several such pairs. And what he tried to do is to find the decryption key, or to decrypt, if unable to find the decryption key, other sphere text. There are other types. We are not going to pursue the crypto analysis much farther. One other thing I want to mention is the different ways of attacking. All right, regardless of the type of information or the the attacker is having. We have what is called the exhaustive search. All right, and this can be done if the key space is small in size. So you could try all possibilities. And this is true for the Caesar sphere and the affine spheres and the additive, multiplicative. All these are easy to use exhaustive search on. However, if we look at the permutation crypto system, the sphere, the key space is actually m factorial. And if you use a big M, then for example 10, 100, and so on, then it will be very hard actually to use the exhaustive search to find what the permutation is. All right, which permutation the encryption is using. So in this case, we use what is called actually the frequency analysis. As you know, in each language, there are some alphabets which are used more often than others, and there are some alphabets which are used less frequent. And the frequencies, by studying different texts, documents, and so on, are known, okay? For example, in the English language, the letter E appears more often than other letters. It accounts for 12.702% of the letters that appear in a general English document. The letter, for example, Z, appears very seldom, and the frequency, the relative frequency of its appearance is 0.074%. So by determining, which letter appears more often, all right, then And of course, using computers, then we can, a lot of these monoalphabetic crypto system can be attacked, and it turns out that they are not actually secure. So in other words, then the next thing to try to do is to make crypto system that prevent or make the applying or using the frequency analysis, less, in other words, not to work, means scramble, for example, the letters. In other words, don't associate with each letter one letter throughout the message. For example, A could go into different alphabets, but of course we need to be able to, when we desphere it, to get to the right corresponding alphabet. All right, so I'm gonna actually stop right here.